We're group number 5, and our topic was the limiting lift of a suction pump. Contrary to popular belief, pumps do not actually suck water up. What they do is they create a vacuum so that there's a lower pressure inside the pipes. And water wants to go from higher pressure to lower pressure. And so when the pump creates lower pressure in the pipes, the atmospheric pressure pushes the fluid into the lower pressure of the pipes. And the higher the initial pressure, the pumps are able to push fluid at greater elevations.
Our hypothesis was atmospheric pressure limits the maximum suction head a suction pump can exert. In ideal conditions, suction pumps can operate with a maximum suction head of about 10 meters or 33 feet. Ideal conditions are pumping at sea level. The pump produces a perfect vacuum, the water is cold, and there's no frictional losses in the suction hose. In ideal conditions, a suction pump will be able to raise water to a height equal to a height that atmospheric pressure would be able to balance a column of water in a perfect vacuum. The force on suction needs to be strong enough to hold the weight you're pulling. Under realistic conditions, a 25% loss in total suction head should be accounted for due to not a perfect vacuum, friction in the pipe and pump, and mechanical imperfections. Maximum suction head can vary depending on density of a liquid. And pipe materials, pipe diameter, and pump efficiency will also affect the suction head.
Okay, so now we're going to delve into an ideal pump. First off, there's no head loss, which means no frictional losses or pressure losses. Next, the internal pump pressure will be 0 psi in order to create a perfect vacuum. Now we'll do Bernoulli. As you can see, there's a big tank assumption. There's velocities cancel out to 0, the pressure is 0, and the initial elevation is 0, which just leaves the P1 over the unit weight. And in turn, you'll get the max height of 10.33 meters or 33.9 feet.
All right, now that we looked at the ideal pump conditions, we're going to delve into a real pump here. So with the ideal pump, you can assume that you have 0 psi because you have a perfect vacuum. But in real life, your pump's not going to be 100% efficient. So you're going to have a 4 psi. You're going to have a little bit of pressure in your pump, which is why you get this. And you convert it to Pascal so you can use it in the Bernoulli. So that gives you 27,571 Pascals. Then you come down here to your Bernoulli equation. So you're going to have a P1 and a P2. Your P1 is going to be your atmospheric pressure, and your P2 is going to be your remaining 4 psi, which is in the vacuum. And then your initial height is going to be 0. Your initial velocity is going to be 0 because you can assume a big tank. And then your final velocity is going to be 0 as well. So you'll get a remaining height, which is going to be your Z2 term. Down here, you basically have change in pressure over your unit weight, which gives you your Z2, your height. And come down here, plug in the numbers to do the calculations. And you find out that your Z2 is 7.5 meters. And then, obviously, you're going to have some head loss due to the fact that your pump isn't perfect. You can calculate that by subtracting your maximum height, which you get from your ideal pump calculation. So you're going to just subtract 7.55, which you get from the real pump, minus your maximum height, which is 10.33. And then you get your head loss as 2.78 meters. And this is also 25% roughly of your maximum height, which is kind of an accepted value that you can get this.
We concluded that varying atmospheric pressure and internal pump pressures creates different maximum suction heads or lift elevations. Under standard atmospheric pressure and ideal pump conditions, the maximum elevation lift will be approximately 10.33 meters. Thank you.